This video will introduce you to the physics behind something called a capacitor, which is simply two isolated conductors of any shape that are separated by some distance. Quite often when we're talking about capacitors, we'll talk about the capacitor plates. We use this term because the most common shape for a capacitor are two parallel plates. However, anytime you see that term plates or hear the term plates, really what we're talking about are the two conductors that make up the capacitance, that make up the capacitor. Saying that they're isolated simply means that they're not connected to any other conductors. When we're dealing with capacitors, we'll quite often talk about the term capacitance. It's a measure of how much charge you must put on the plates to produce a certain potential difference between them. In other words, or really, in symbols, that's saying that capacitance, which we use a capital C for, is equal to the charge divided by potential difference, Q over delta V. When we're dealing with the charge in this case, we're looking at the magnitude of the charge on one of our two plates or on one of our two conductors, and delta V is the potential difference between them. We know that charge is measured in coulombs, and we know potential difference is measured in volts. A coulomb per volt is otherwise known as a farad, which is the unit that we use for capacitance. It has a symbol of a capital F. Quite often when dealing with capacitors, we're talking in terms of microfarads, nanofarads, maybe millifarads, but it's very rare to have a capacitor that is in terms of actual farads. It's a very big unit. One thing that's really important to know is the process by which a capacitor is charged. In other words, a process by which the capacitor is made so that one plate is positive and one plate is negative. Because of the process by which it is charged, the plates will have charges that are equal in magnitude but opposite in sign. That's why when we're using this equation, the capacitance is Q over delta V. This Q is the charge on a single one of the plates. Let's talk about that method by which a capacitor is charged. What I have drawn here is a simple circuit diagram for a capacitor connected to a battery. That's what this symbol at the bottom here represents, a battery. A battery is a source of a potential difference. Really, I could draw this exact same circuit with, rather than having a battery there, having maybe a plug into a wall outlet or something like that. Some source of potential difference. When we connect this capacitor to a battery, that battery, which has a potential difference, causes electrons to leave one of the conductors in our capacitor and move to the other one. It'll do so in such a way that, let's say we have electrons on this plate. Those electrons will travel along this wire, through this battery, and go up to this conductor and stop, because there's no possibility of them jumping through this gap between the two conductors. You'll notice that these are drawn as two parallel plates, but just because they're drawn as two parallel plates doesn't mean that my capacitor is made of parallel plates. This same drawing would work for if I have two spheres, for example, that are separated by a distance. The process of the electrons traveling through the wire, through the battery, and up to the other plate is the process of charging a capacitor. We'll learn more in the future about how much time it takes for this to occur and what affects the time that it takes for this to occur. But eventually we'll get to the point where our capacitor is fully charged. In other words, where the movement of electrons stops. That does not mean that all of the electrons in the capacitor have moved to the other plate. Rather, the number of electrons that move is dependent on the voltage of the battery. Remember, voltage is just another term for potential difference. I have a little simulation here showing you a bit more about what happens as a capacitor is charging. So what we have here is a battery, just like was shown in our diagram, and a capacitor, as you can see here. And we have a switch that right now is in the open position. Because it's in the open position, there's no conducting path that includes this capacitor and the battery. However, as soon as I move it to a position where it includes both objects, you saw that all of a sudden I had some charges moving. I had those electrons from this part of my capacitor and this plate of my capacitor moving through the wire, through the battery, up through this switch, into the other side. So I got it to the point where I have one negative plate and one positive plate. Again, positive, not because of the movement of positive charges, but because of the lack of electrons. Now when I open my switch, all those charges stay there. They have no path to go from the negative plate to the positive plate until I move the switch into the other position. And you can see that when I did so, when I moved the switch into the position that connected to the two conductors within the capacitor, all of those electrons traveled around that path and went back where they originally came from, once again making the capacitor neutral. I'll show that process one more time in case you missed it the first time. Here I'm charging my capacitor. Now my capacitor is fully charged, and it'll remain fully charged until I provide a path for those electrons to travel back to their original plate. The big key thing to remember here is that the capacitor will remain charged until it has that path to travel through. And typically, when we use capacitors in electric circuits, that path that you use to discharge the capacitor converts that electrical energy that the electrons have into some other form of energy. Perhaps that other form of energy is light, or maybe a sound. Light may happen with a flash in a camera, for example. In class, we'll learn more about how to find the capacitance of a particular capacitor, like parallel plate capacitors, or spherical or cylindrical capacitors. We'll also learn about what happens when capacitors appear in circuits with other capacitors, or possibly with resistors.